Welcome. Tonight, I want you to close all the windows of your mind and embark on a journey guided only by my voice. Set aside the exhaustion of the day, the unfinished tasks, and all the voices cluttering your thoughts. Now we travel to an era where time flows much slower, where the night speaks only with the stars and the wind. Close your eyes and imagine yourself on the edge of a vast, silver sea of sand. The sky is so clear that you can see the river of light, the Milky Way, stretching from one horizon to the other. This is the Silk Road, the legendary path where millions have trodden for millennia, leaving a story with every step. Now we begin a calm walk into the Silk Road was not merely a trade route, but a complex logistical network that began to take shape as early as the centuries before Christ. To understand the functioning of this road, one must first examine the structure of the caravans and the biological resilience of the pack animals used. A caravan typically consisted of 50 to 100 camels. These were primarily Baktrian camels, double-humped. This species could survive the Central Asian winter lows of 40 degrees and the scorching summer heat, thanks to the fatty tissue stored in their humps. A camel's average daily speed did not exceed 4 kilometers per hour, which meant a caravan could cover only 25 to 30 kilometers in a single day. Caravanserais, located along the transit routes, were constructed at specific intervals. These distances were calculated based on a 9-hour march, the maximum distance a camel could travel without water. The architectural design of these caravanserais was built entirely on defense and functionality. Usually following a square or rectangular plan, these structures were surrounded by high, thick stone walls without windows to protect against outside attacks. Upon entering the inner courtyard, the ground floor contains sections for securing camels and cargo, while the upper floor housed small dim rooms for merchants to lodge. Heating in these rooms was provided by a system of clay pipes, kunk, hidden within the walls, which was a highly advanced engineering example for that period. When looking at the technical side of trade, we see that silk was used not just as a fabric, but as a currency. During China's Han Dynasty, a portion of civil servants' salaries was paid directly in bolts of silk. A bolt of silk had a standardized length and weight. As it traveled westward, the value of this silk increased exponentially. Transportation costs, transit taxes levied by local emirates, and the wages of guards hired against bandit attacks accounted for 80% of the final sale price. By the time it reached the Roman Empire, 1 pound of pure silk had become equivalent to 1 pound of gold. This economic imbalance led to debates in the Roman Senate regarding the drain of the empire's gold reserves to the east due to silk consumption, and even resulted in the enactment of sumptuary laws prohibiting the wearing of silk garments. The demographic structure of the cities along the route was also shaped by this commercial cycle. Samarkand, for instance, was not just a stopover, but a center for paper production. Following the Battle of Talas in 751, Chinese papermakers taken as prisoners professionalized the production of paper from linen and hemp fibers here. This was a technical revolution that accelerated the spread of knowledge and bureaucracy. In the city's marketplaces, not only goods were exchanged, but also letters of credit and bills of exchange were issued. A merchant could cash a document obtained in China at a money changer thousands of kilometers away. This primitive banking system minimized the risk of caravans carrying gold bullion. The botanical details of the spice trade are equally technical. Black pepper was called black gold at the time because it grew only in specific regions of India. The drying process, humidity levels, and storage conditions directly affected the quality of the spice. When Venetian merchants received these spices at the ports of Alexandria, they meticulously weighed every sack and used specialized methods to check for adulteration. These processes formed the cornerstones of what we know today as international trade law and customs procedures. When we examine the logistical infrastructure of maritime trade routes, we can clearly see how small but vital technical changes in shipbuilding technology influence the speed of intercontinental commerce. The dhow-type vessels used in the Indian Ocean were constructed without nails. Instead, planks were sewn together with ropes made of coconut fibers. This flexible structure ensured that the ship would not shatter upon hitting coral reefs, but would instead absorb the impact. The lateen sail, the rigging structure of these ships, provided the ability to maneuver regardless of the wind direction, a technical revolution that prevented caravans from waiting months for the monsoon winds to shift. A single ship had a carrying capacity of approximately 400 tons, which was nearly 10 times the load a caravan could carry. Consequently, cost calculations for maritime routes differed fundamentally from the insurance and protection costs of overland routes. By the 14th century, the taxation of trade and the maintenance of customs records had become the most significant bureaucratic endeavor for centralized states. In ports controlled by the Mamluk Sultanate, a tiered taxation system was applied based on the type of cargo when a ship docked. Luxury goods like silk and spices were taxed ad valorem, based on value, while bulky goods like grain and timber were taxed by weight. Customs officials would open every bale to inspect the quality of the goods and subsequently seal them with a state stamp. This sealing process was a security protocol developed to prevent fraud as the goods changed hands before reaching the market. The ledgers in which these records were kept constitute the most concrete sources used today for the economic data analysis of that era. Another technical challenge faced by caravans on the Central Asian plains was the storage and transportation of water. Leather skins, water skins, were used for desert crossings. However, to reduce the evaporation rate of the water inside, the outer surface of the leather was regularly greased with animal fats. The rational use of water was the most critical duty of the Caravanserais, caravan leader. The daily water requirement of every individual and animal was calculated in milliliters, and intelligence regarding the depth and salinity of wells along the route was gathered in advance. At certain strategic passes, Qanat, carries systems, underground water channels, were kept under maintenance for thousands of years. These channels consisted of underground tunnels with a specific gradient and vertical ventilation shafts that allowed water to be transported for kilometers without evaporating. The construction of these tunnels required an advanced knowledge of trigonometry and engineering for that time. Changes in the monetary system are another monotonous but critical factor determining the pace of trade. The Byzantine Empire's solidus gold coin functioned as a global reserve currency for centuries due to the stability of its purity. However, with the transition to the dinar and dirham system in the Islamic world, The parity difference between these two systems led to the emergence of serifs, money changers, as a professional class. These money changers did not just exchange currency, they also issued payment orders called suftaja, the ancestor of today's check system. These documents possessed a level of security that was impossible to forge, thanks to their specific seals and calligraphic styles. A merchant could deposit gold in Baghdad and receive its equivalent in Cairo after a commission fee was deducted. These financial instruments increased the volume of global trade by 30% by eliminating the risk of theft during the physical transport of money. Technical studies on the packaging and storage of commercial goods form the basis of today's logistical standards. For instance, in porcelain transportation, Chinese masters placed porcelain vessels in wicker baskets and filled the gaps with rice husks or bean sprouts to prevent breakage. When these filling materials became damp during the journey, they would swell, completely preventing the porcelains from touching one another. Similarly, glass bottles containing perfumes and precious oils were kept in wax-coated leather cases to protect them from the degrading effects of light. These packaging techniques ensured that the goods maintained their quality even after thousands of kilometers, but they also increased shipping fees due to the additional weight of the packaging. Such cost-benefit analyses were part of the complex mathematical calculations every merchant performed before an expedition. The mechanical structure of looms and the technical standards in textile production were among the most fundamental factors determining the supply side of Silk Road trade. In particular, the transition from vertical looms to horizontal treadle looms increased a weaver's daily production capacity by approximately 30%. To increase the breaking strength of yarns during the weaving process, sizing hashalama techniques were used, typically involving a mixture of cereal starch or animal glues with specific ratios of water. This starch layer minimized the frictional resistance of the yarn on the loom, preventing surface irregularities on the fabric. The MAMI unit, which determined the quality of silk fabrics, expressed the weight per unit area and the thread density. While fabrics with a high MAM value were more durable, their production time was longer and the amount of raw silk used was greater, which directly affected the final product's taxation bracket. When examining metallurgy and ore extraction techniques, the process of processing iron and transforming it into steel in the medieval world relied on extremely precise heat treatment procedures. For the production of crucible steel, crucibles were made from high heat-resistant clay and filled with iron ore along with plant-based waste as a carbon source. This mixture was kept for days in furnaces where air circulation was controlled. The hardness level of the resulting metal varied according to the temperature and chemical composition of the liquid used during the quenching sous verme process. Some bladesmiths preferred using oil or animal fats instead of water to maintain the metal's flexibility. These technical details were the sole factors creating price differences in the arms trade. For a sword's durability depended on the regularity of the crystalline structure of the carbon atoms within it. In mining operations, the timber shoring and scaffolding systems used for the fortification and ventilation of underground tunnels were a result of static calculations. To solve the flooding problem encountered as depth increased in silver mines, manual pumps operating on the principle of the Archimedes screw were used. Mine workers worked in shifts to gradually evacuate the water to the surface. The enrichment process of the extracted ore consisted of crushing and washing stages. The ore was passed through water channels, allowing heavy metals to settle at the bottom based on density differences. This process necessitated a continuous water source near the mining site, leading logistically to the establishment of permanent settlements around the mines. Food preservation techniques and the chemical use of salt were of vital importance in long-distance trade. Salt was not just a flavoring agent, but a dehydration agent that prevented the decomposition of organic matter. The dry salting or braining methods applied to ensure that fish, meat, and certain vegetables could be transported for long periods created high osmotic pressure environments where microorganisms could not survive. Since the purity level of the salt directly affected the preservation period, the price difference between block salt brought from the Sahara Desert and sea salt was determined by their magnesium and calcium ratios. While forming their rations, trade caravans preferred dried fruits as carbohydrate sources and high-protein legumes. For the weight-to-energy ratio of these foods was much more advantageous than fresh foods. The standardization of weights and measures used in the ancient world formed the legal infrastructure of trade. Every major commercial center would engrave its own standards of L, arshun, or pound, libre, onto stone tablets and hang them at the entrance of the marketplace. Merchants who deviated from these standards faced heavy penalties. Scales used as weighing instruments were manufactured from bronze, and their sensitivity settings were periodically checked by customs officials. The carob seed, carat, used in weighing precious stones, had become a global standard because its weight in nature almost never changes. This technical stability allowed merchants who spoke different languages and held different beliefs to meet on a common mathematical plane, forming the first building blocks of the global economy. The chemical composition of construction materials and mortar technologies used in the ancient world are the most fundamental engineering data determining the durability of permanent structures along trade routes. The binding material known as Khorasan mortar, obtained by mixing lime, sand, terracotta powder, and occasionally organic fibers, possessed hydraulic properties. This allowed the mortar to harden further upon contact with water, increasing the resistance of Caravanserais against foundation seepage. Temperature control during the lime slaking stage directly influenced the carbonation process within the mortar, enabling structures to maintain their static balance for millennia. In brick production, the firing duration of the clay and the oxygen levels within the kiln determined the brick's pore structure and, consequently, its thermal insulation coefficient. These technical details created a passive climate control system that stabilized the extreme heat of the day and the extreme cold of the night within desert lodging units. The production differences between parchment and papyrus, the information storage technologies of the time, were decisive factors in calculating bureaucratic costs. While papyrus was produced from the stem fibers of Cyperus papyrus, a plant native to the Nile Delta, parchment was obtained by soaking animal hides in a lime bath, stretching, and scraping them. The production of parchment required significantly more labor and raw material costs than papyrus. However, the fact that parchment could be written on both sides and folded allowed for archives that were more durable and logistically compact. While the transportation cost of a caravan load of papyrus was high due to the product's volume, records in parchment form could be kept in a much more condensed structure. This technically explains why contracts and title deeds used in long-distance trade were predominantly written on parchment. The casting techniques of ship anchors and the metal alloys used are other mechanical elements determining the safety coefficient in maritime transport. Stone anchors used in antiquity were eventually replaced by combinations of cast iron and wood. Keeping the carbon ratio low during the forging of iron anchors increased the metal's resistance to corrosion in seawater. The form of the anchor was optimized for different seabed types. Models with wide flukes were preferred for sandy bottoms, while thinner, sharper models were used for rocky terrain. This technical specialization reduced the risk of a ship dragging anchor during storms, directly affecting the insurance premiums and risk analyses of the precious cargo being carried. The design of distillation apparatuses used in perfume and essence production represents the first instances of chemical science transforming into commercial power. The length and inclination of the cooling pipes in these devices, called alembics, determined the purity level of the resulting essence. Gradual distillation, performed by utilizing the differences in the evaporation temperatures of plant oils, allowed for products of varying qualities to be extracted from a single raw material. For example, the dense oil, a tar, obtained from the first distillation of rose water, was a commercial commodity more valuable than its weight in gold. The expansion coefficients of the glass vessels storing these products were optimized using controlled cooling, annealing techniques to prevent the glass from cracking during hot desert crossings. Road construction techniques in the ancient world, particularly during the Roman and Persian empires, relied on drainage and multi-layered soil engineering. When a road was constructed, the large stone blocks, statumen, placed at the lowest layer, followed by smaller stones and the flat surface paving on top, distributed the pressure applied to the ground by heavy-duty wheeled carts. Drainage ditches dug on both sides of the road prevented rainwater from seeping into the roadbed, thereby preventing the ground from softening and collapsing. These engineering standards ensured that caravans could travel at the same speed, regardless of the season, increasing the predictability of trade and providing a foundation for the secure execution of forward sale contracts. With the transfer of paper production technology from Central Asia to the Middle East, the use of water power in milling mechanisms elevated production capacity to an industrial level. In a paper mill, the circular motion from the water wheel was converted into a vertical striking motion via an eccentric shaft. This mechanism operated massive hammers that beat flax and hemp fibers for hours to turn them into pulp. The degree of fiber disintegration is the fundamental technical data determining the paper's absorbency and ink-holding capacity. When the pulped fibers were poured into screened molds, the drainage rate of the water influenced the paper's weight, grammage, and surface smoothness. The animal gelatin bath used during the drying process to prevent paper sheets from sticking together created a protective layer on the surface, preventing ink from bleeding into the fibers. These technical standards were the most vital archiving parameters, ensuring that commercial records remain legible for many years. The press mechanisms used in olive oil extraction represent one of the most common applications of pressure physics in the ancient world. Harvested olives were first crushed into a paste in vertically rotating stone mills. At this stage, crushing the olives without breaking the pits was a vital detail to prevent the acidity level of the oil from rising. The resulting paste was filled into wicker baskets, which were stacked and put under pressure. The oil obtained from the first pressing had the lowest acidity and the highest nutritional value. The screw mechanism used in the pressing process distributed the applied force over the surface area, ensuring the separation of oil from the fibers. The temperature of the hot water used in this process determined the balance between preserving phenolic compounds and increasing yield. During the settling of the oil in tanks, the specific gravity difference allowed water and sediment to sink to the bottom while the pure oil remained on top. This separation process was a technical necessity, determining the oil's shelf life and durability along trade routes. The chemical properties of mordants used in wool and silk dyeing processes are the primary elements determining the color, fastness, and market value of textile products. Natural dyes lack the ability to bind directly to fibers. Therefore, a chemical bridge was established between the fiber and the dye molecule using mordants such as alum or iron sulfate. The pore structure of the fabric soaked in an alum bath became suitable for trapping dye pigments. The temperature gradient in the dyeing vats was increased incrementally to ensure that pigments penetrated to the very core of the fibers. In the use of madder, rubia tinctorum, the shade of red obtained according to the soil's pH level, served as a sort of signature indicating the fabric's region of origin. The fixing processes performed after dyeing were a quality control stage measuring the fabric's resistance to sunlight, UV resistance, and washing. The margin of error in these processes was critical enough to have the value of an entire caravan load of fabric. Glaze technology used on glass and ceramic surfaces is a layer of glass obtained by mixing silica, lead oxide, and various metallic pigments in specific proportions. During firing, the glaze must expand and contract at the same rate as the ceramic body. Otherwise, structural defects known as crazing or shivering would occur. Whether the atmosphere inside the kiln was oxidizing, oxygen-rich, or reducing, low oxygen, completely changed the color of the glaze. For example, iron oxide produces yellow-brown tones in an oxidizing environment, while it takes on greenish, celadon tones in a reducing environment. This capacity for chemical manipulation symbolized the technological superiority of the workshops. Glazed vessels were not only aesthetic, but also functional technological marvels that allowed for the hygienic storage of liquid foods thanks to their impermeable surfaces. Weightlifting and transport mechanisms in the ancient world relied on complex combinations of pulley and lever principles. Polyspastos type cranes used in Grand Temple constructions or loading operations at ports featured gear systems that could multiply the force applied by a single person 5 or 10-fold. The ropes of these cranes were manufactured by tightly braiding hemp or flax fibers and were regularly lubricated with tallow to prevent wear caused by friction. The inclination angle of the crane arms was adjusted according to geometric calculations to maintain the static center of the load. This logistical capacity represented the most advanced mechanical engineering applications of the period, making it possible to load marble blocks weighing tons or massive commercial amphorae onto ships. The construction of bridges providing river crossings on trade routes is the most concrete indicator of the static calculation capabilities of ancient engineering. The stability of an arch bridge depends on balancing the horizontal thrust force exerted by the central uppermost stone, known as the keystone, onto the adjacent stones. The geometry of the arch form was generally designed as a full circle or a segmental arc. The objective of this design is to transmit the vertical load imposed upon it to the ground via the arch piers. To ensure the piers could resist the current in the riverbed, triangular structures called starlings, cutwaters, were built. These structures split the hydrodynamic pressure of the water, preventing the erosion of the piers and the scouring of the ground beneath them. The scaffolding systems used during construction consisted of wooden frameworks designed to carry the entire load until the arch was completed. The moment the keystone was placed, the structure locked under its own weight, and the static function of the wooden scaffolding concluded. The pozzolanic concrete used in the underwater sections of these bridges and harbor breakwaters was one of the most important technical secrets of Roman engineering. This mortar, obtained by mixing volcanic ash, pozzolana, with lime and seawater, possessed the property of hardening through a chemical reaction underwater. Unlike modern concrete, the molecular structure of this concrete became even more durable over time as it interacted with seawater, forming microscopic crystals within. In harbor constructions, waterproof enclosures made of interlocking piles known as cofferdams were used to evacuate water. Once the water inside these sections was pumped out, concrete was poured onto the dry bed, and the foundation of the structure was fixed to the river or seabed. This technology enabled the construction of harbors resistant to storms and high wave energy, forming a logistical foundation that allowed maritime trade to continue uninterrupted. Mechanical power transmission, windmills, and metallurgical furnace control. The wing design of windmills and the process of converting wind energy into mechanical work involve early applications of aerodynamic principles. The blade angle of a windmill must have an inclination of approximately 15 to 20 degrees relative to the direction of the wind. This angle creates a pressure differential on the blade surface, initiating circular motion. The rotational speed of the blades is transmitted to the vertical shaft via large gear wheels, lantern gears, on the main axle. These gear systems were typically manufactured from hard woods like hornbeam or oak, which have low friction coefficients, and were regularly lubricated with tallow to prevent wear. Gear ratios were mechanically calculated to convert the variable speed of the wind into the constant speed required by the millstone. The depth and arrangement of the furrows on the surface of the millstone ensure the degree of grain crushing and the grinding of flour without overheating. This is a critical technical parameter for preserving the protein structure within the flour. In medieval metallurgical foundries, the control of the temperature inside the furnace and the purity level of the metal relied on visual observation techniques and the manipulation of airflow. In this era, before thermometers, masters estimated the temperature by observing the color of the metal. Dark red corresponded to approximately 700, bright orange to 1000, and white light to 2200 degrees Celsius. The bellows systems providing air to the furnace were operated by mechanical arms driven by water wheels. This ensured a continuous and high-volume influx of oxygen into the furnace, increasing the combustion efficiency of the coal. During the casting process, the flow rate of the liquid metal into the mold had to be adjusted in a controlled manner to prevent the formation of air bubbles. The moisture content of the sand and clay mixture used as the mold material affected the cooling rate and the crystal structure of the metal. If cooling was too rapid, the metal became brittle. If too slow, it remained soft. These annealing and heat treatment processes were the sole engineering criteria determining the mechanical durability and, consequently, the commercial lifespan of the manufactured tools. In the ancient world, the optical properties of glass and its capacity to refract light were directly dependent on the levels of impurities within the glass and the molecular alignment determined by the cooling rate. The smoothness of a glass surface and its light transmission coefficient were increased by minimizing the amount of iron oxide within the sand used during the production phase. Iron oxide imparts a natural green tint to glass. To neutralize this tint, manganese dioxide, also known as glassmaker's soap, was used. This chemical interaction altered the light absorption within the glass, allowing the material to appear more transparent and colorless. The surface tension of the molds into which the glass was poured was coated with pre-lubricated graphite or thin clay layers to prevent the formation of micro cracks on the surface during cooling. The radius of curvature of convex glass lenses used for optical purposes was adjusted at the micron level through manual grinding and polishing processes. For this polishing process, finely powdered siliceous rocks called tripoli or pumice powders were mixed with water to form an abrasive paste. In the development of mirror technology, technical studies on the reflection coefficients of metallurgical alloys were decisive. Due to the high cost of silver mirrors, the reflective surfaces most frequently carried in trade caravans were high-tin bronze alloys known as speculum metal. This alloy was generally prepared with a ratio of 2 parts copper to 1 part tin. Although such a high tin content made the alloy extremely brittle, it increased the reflection capacity of the surface after polishing to a level close to that of silver. To delay the oxidation of the metal surface after casting, a thin layer of beeswax or resin was applied to the surface to cut off contact with air. In later periods, for mirrors made by pouring a thin layer of lead or tin behind glass, amalgam techniques were used to ensure the metal adhered perfectly to the glass surface. During this process, temperature control was critical to ensure that the metal layer was distributed at a homogeneous thickness, usually at the level of 1/10 of a millimeter, across the glass surface. The hygroscopic properties of the wood types used in shipbuilding and resin coating techniques are another engineering protocol applied in maritime trade to keep a ship's water intake, displacement, constant. The fiber density of the oak wood used in the ship's keel was measured by the number of vessels per square centimeter in longitudinal sections. Kiln drying or natural seasoning processes performed to reduce the water content of the wood to below 15% were carried out to minimize the expansion margin when the ship entered seawater. The process of caulking, applied to the ship's outer hull, was performed by saturating flax fibers with a mixture of pine tar and tallow, and then driving them between the planks. This composite structure provided water tightness as a mechanical barrier, while allowing the ship to flex under dynamic loads. The boiling point and viscosity of the tar were kept constant between 90 and 100 degrees Celsius to ensure deep penetration between the fibers. This technical maintenance also chemically prevented organisms, barnacles, that reduced the ship's speed and fuel energy efficiency from adhering to the wood.